Okay, so hopefully now you've had a chance to play around with the butterfly applet and you have a good sense of what the theorem states. Here's what the theorem states. It says, suppose that chords PQ and RS of a given circle meet at the midpoint M of a chord AB. So if X and Y are the points where PS and QR meet respectively, then XM equals YM. So maybe we should draw a quick picture of this. I have one drawn towards the end of my slides here. So I'll just show you the picture that I have drawn rather than watch me painstakingly draw it again. So here's a picture of what the theorem states. What we're given is that AM and MB are equal in length. So, we're given that AM is equal to MB. And then all the rest of the parts and pieces are just as shown. PQ and RS are chords of the circle that meet at M. And then we go ahead and construct PS and RQ and let those two segments meet AB at X and Y respectively. What we want to show in this theorem then is that XM is equal to MY. Hopefully that's what you saw when you played around a little bit with the applet. That those two chords sort of mysteriously seem to, or I shouldn't say chords, those two segments mysteriously seem to maintain the same length, no matter where I put A or B or P or S or R or Q. I mean, it's quite remarkable if you think about it. There are really 6 points here that we have to play with, A, B, P, R, S, and Q. The only points that are really then determined are X, M, and Y, and it just so happens that XM equals MY. Okay, so how to go about proving it? I've seen this done a couple different ways, and I'm going to go ahead and follow the book's proof. What the book does is instead of diving in and solving the theorem, they prove a small, or a fairly, I should say, difficult lemma to begin with. That's actually kind of interesting. It's actually a more useful theorem, a more broader theorem than the butterfly theorem, and it's this lemma 3.14, and it says in the figure segments of length x, y, u, v, and s and t are marked. If the angles marked are equal, then x squared over y squared is u, v, s, t. So just sort of zoom in. X squared, I guess this little piece divided by y squared, this other little piece, is equal to the product of u times v divided by the product of s times t. So it seems like quite an interesting piece. One of the things you should notice is that this doesn't lie in a circle anymore, right? And so it seems like it might be a broader result than the butterfly theorem. So in a sense, the butterfly theorem would be a simplified version of this, perhaps. Okay, so let's go ahead and dive in and prove this little piece, and then we'll see if we can apply it to the butterfly theorem. So I have a picture drawn, I guess, just on a white background of the figure, which I copied over here to our proof. So let's go ahead and dive in. This is proof of theorem 3.14. I'll just do a sketch of what's going on here. So it turns out that what we want to show is that x squared over y squared is equal to uv over st. Okay, so the difficult part about this is that there really isn't a lot to go on, right? We can start sort of drawing in some angles that we know would have to be, I guess, the same in measure. Like, for example, we know that since the two given angles are congruent, and here in the middle we have sort of these red angles here and here, that means that these blue angles here and here would have to be the same. So certainly we could say that the two triangles that we see here, the two larger triangles to the left and the right, would have to be congruent, or sorry, similar because of angle-angle similarity. But really, you don't get very far from that. And so the right thing to do here is actually to add a bunch of helper lines, and these helper lines seem to be sort of everywhere in every proof of the butterfly theorem. So I'll just go ahead and draw them in now. It turns out that the right thing to do is, well, let's go ahead and first label some links, or some vertices. Sorry, we'll call this A. I'll do it in black. We'll call this big A. We'll call this big B. We'll call this big C. And we'll call this big D. We'll call this big X and this big Y. I'll try to distinguish that between small x and small y, which are lengths. And then, of course, we'll call this one in the middle M. So not given here that xm equals my, right? And then what seems to be the right thing to do always is to add some helper lines. So I'll go ahead and add these helper lines in green just so we can distinguish them. One thing to do is to add a helper line here that's parallel to this one. And while we're at it, we might as well do the same thing here. Again, parallel. So we can say that those, I guess, 3 lines are parallel. I'll go ahead and sort of draw over the top of this one a green one so we can kind of keep it all straight in our mind. Okay, so we could add those parallel lines. If we add those parallel lines, then what's going to happen is we're going to have some new points to label. I'll call that point T. I'll call this point S. But you might have noticed that you don't have to just go that direction, right? We could add some that are parallel to BC as well. So let's do that next. I'll add it in a different color. I don't know, how about some sort of a purple or a pink, maybe a nice pink. Okay, I'll add this in pink. So if we added some points that were some lines that were parallel to BC to this drawing, it might make sense to add one here. And it might make sense to add one here. So again, we add some lines that are parallel here and here. My drawing has made it pretty hard to distinguish that there's a point R there. Let's call this, I'll call this a point, like U here. And now all of a sudden we have all kinds of similar triangles that seem to sort of pop out at us. I'm going to just go ahead and label some angles that I know would have to be the same. Let's see. So I don't know. How do we want to go about this? Let's call this blue angle E. And I'll do all the angles maybe in blue. How's that sound? Get our blue back. So I'll call this one E. That makes this one E. So now, let's see, let's see here. I don't know, here at the center we have a couple angles that are the same. Let's call this one on top A. So that makes this one A. Let's call this one B. So that makes this one B here. That's by vertical angles. Okay. So now if we sort of think about the line MY as a transversal of the 2 green lines, then this one up here has to be B by alternate interior angles. And if we think of MY as a transversal on parallel lines that are pink, we can say that this one has to be A. Okay, so let's see. Same reasoning goes over here. So this one would have to be B and that one would have to be A. And let's see, so let's label a few more here. If you look along AB is transversal of the two pink lines, which means that this little guy in here has to be E as well. So by corresponding angles. And if we call, let's say, this one, let's say if we call this one E, then that one up there has also got to be E. I don't know, let's go ahead and call this one here C. And by, again, alternate interior angles, where the green line is acting as a transversal and the parallel pink lines, this one is going to have to be a C as well. And if this one is D, then again, by alternate interior angles, this one would have to be D as well. I think that's probably enough to get us good and started. I mean, right away we get lots and lots of similar triangles, just looking at angles. So I'm going to go ahead and name a few similar triangles and work from there. So let's go ahead and do it. I think I kind of want to do it down below here. See if I can keep it in view. So the first one I want to name is, let's see, triangle XRM is certainly similar to triangle YUM. So that's nice, triangle YUM. XRM is up here above. It has angles A, E, and B, AC and B, sorry. XRM, so, and down below, I guess, the trends, or I guess the line XY, we can see that YUM also has angles A, C, and B, so those ones have to be similar by angle. And in those triangles, I can see that, let's see, RM would correspond to UM. And those two side lengths, RM and UM, would be in proportion X to Y. So right away we got one piece that we like, an X to Y. But notice that we can play off of the other two similar triangles. So let's see, this would be XSM, similar to YTM. So XSM is going to look like, maybe I should draw some of these in as XSM is this one, right? And it's parallel to, or sorry, it's similar to YTM, that one right there, right? So those two, of course, are similar too. And we can play the same game with X and Y. And in this time, what I'm going to say is that SM is a TM. Oops. As X is to Y. So if I take these two results together, then what I get is I get X squared over Y squared when I multiply the right-hand sides. And when I multiply the left-hand sides, I guess I get RM on top times SM on top over UM times TM. So I feel like I'm kind of getting somewhere. At least I have, sort of the left-hand side of my expression, but it's certainly not, RM and SM are not U and V. We can see that, RM is this length, SM is that length, and yeah, it's definitely not U and V. So we need to do a little bit more results. So let's see. You can use another similar triangle in here. It's going to be triangle AXR, similar to triangle CYT. Where is AXR? Let's see. So AXR, I guess if we look really closely here, it's this one. I'm sorry, my drawing is not very nice in terms of sort of AXR is that guy, CYT is that guy, and I guess we can see that they would have to be similar. They both have an angle E and a shared angle A and C, congruent by hypothesis. So by angle, those are certainly similar. And okay, so let's go ahead and see what sides we're going to use there. So what we get there, AXR, similar to CYT, we end up with AX would be to CY as XR is to YT. And one thing to notice is that AX is to CY. Let's see, so AX is the same thing as our little letter U, and CY is the same thing as our little letter S. So we're getting someplace here. So this would be the same thing as U is to S. And XR is to YT. Well, I mean, the thing is that XR, this segment right here, is to YT. This segment here. We're going to replace that with this segment here and this segment here. And certainly we can see they look like they're going to be the same lengths. XR the same as SM and YT the same thing as MU. But the rationale for that is that those sides are opposite sides in a parallelogram. We have two little parallelograms there in the middle of the figure. So we can use those properties of parallelograms. So that's what I'm going to do next. I'm going to say that XR is to YT as XR is going to be the same thing as its opposite sided of the parallelogram, which is going to be SM and UM. I'm going to call this equation 2. I'm going to call this one equation 1. So what I see here is that I've got a little piece right here, SM, UM. That's my SM and UM. If I could kind of play the same game here to find the other piece, right, RM and TM, then I might be in good shape, right? Because I can see that SMUM I can replace with U over S. Sorry, I should do that in red. Okay, well, it turns out that you can just play this game by a similar argument. So we get that U is to S as SM is to UM. Like if we kind of think about U is to S as SM is to UM, then let's see what would, I mean, just kind of think to yourself of like sort of flipping this over, right? We took the top two pieces, U and S. Let me just highlight some things. U is to S as SM is to MU, right? So it kind of seems to make sense that we could just have played this game in sort of an upside down sense, that v to y, v to t would be the same thing as rm is to rt here, right? So that's the idea. We would just play the game sort of in the opposite direction and use a similar argument. I'll erase these highlights and just say, instead of marching through it by similar argument, we could get that v is to t as rm is to tm. Call that equation 3. And now I can see that that's the blue piece that I needed here, right? Blue piece I can replace by v to t. So we're at the spot where we can then go ahead and reach our conclusion. So I would just say something like substituting 2 and 3 into 1, we get that x squared over y squared is equal to v over t times u over s, which is the same thing as uv over st, which is what we wanted to show. Okay, so we've got this little lemma now that works for this sort of a situation. Anytime we have the equal angles up there at the top of this sort of triangular figure, then the square of x over the square of y is going to be the product of uv divided by the product of st. Turns out that this makes it quite straightforward then to prove the butterfly theorem. So we'll go ahead and now prove the butterfly theorem. So here's our proof of theorem 3.13, the butterfly theorem. It says, we're given that M is the midpoint of the chord AB, and we have chords PQ and RS meeting at M. We draw in PS and RQ. We get an X and a Y, and mysteriously XM equals MY. Well, the first thing to note in the proof since, let's see, angle P is equal to angle R, we can apply theorem 3.14. Does everybody understand why angle P is equal to angle R? These both subtend the same arc on the circle, right? So angle P and angle R both subtend this arc on the circle. So since those two subtend the same arc, they've got to be equal in measure. Okay, so we'll apply theorem, or I guess it's lemma really, 3.14. And what would we get? So we would get something like this. We get xy, I should maybe call this big X, y squared over ym squared. Oh, it should be xy, it should be xm, right? xm squared over ym squared is going to be the product of what's on the outside on the xm side. So it'd be px over the product that's on the y side, so it'd be ryyq. So that's one result we have here. But one thing to note is that since we're on a triangle, on a circle, that we have this theorem that says that px times xs, let's see here, is ax. So let me just highlight some things. px times xs would be the same thing as ax times xb. So we kind of think of those two segments. What we can kind of think of is that they both belong to sort of their own similar triangles like this. So one of the things we could say about those similar triangles is that, let's see if I kind of take similar sides. See, px would be to, let me see, how do I want to do this? Px would be to xb. So px is to xb as ax is to xs. So sort of thinking about those similar triangles, we can say that everybody understand why those are similar. They angles subtend the same arcs and circles, and we got vertical angles in the middle. So so one statement I could make using, I'm going to go ahead and erase those highlights. I could say something like this. I could say, well, if I want to replace px times xs, I could replace it with ax times xb. So that's one way I could replace px times xs. If I look at ry and yq, I can kind of play the same game there. So I'll use kind of a green ry and yq. Well, I could replace that with this length to this length because I could draw some similar triangles in there. And ry to yq would be the same thing as by to ya. So I'll go ahead and replace those in the next step. So ry to yq, the thing that's on the denominator down there, could be the same thing as by times ya. If you want to look it up, we actually did prove a theorem back in chapter 1, theorem 1.35. But really it just relies on a little argument of similar triangles, okay? So we're at a kind of a nice spot. We've at least got xm and ym related to ax and x, I guess, segments that are along AB, pieces of AB, right? So I can say by substitution, we have that I'll go back up here, xm squared, ym squared. It's going to be the same thing as on top. Px xs we can replace with ax times xb. And on the bottom we can have by times ya. And what we're really trying to show is right, that these two inner distances, I guess it's, we'd really like to talk about xm and my, right? And we don't have any of those, but we can get at it now if we sort of use some algebra. So now assign, I don't know, let's assign x to be equal to, let's let x be, little x be this distance, oops. And we'll let little y be equal to this distance, and we'll let little m be this distance, which means that this one is also little m. And we can now work in this fact that m is the midpoint, I guess, of AB, and somehow see if we can get somewhere with the proof. So let's just think a little bit about what we have here. If we assign x to be xm and y to be equal to my, and little m to be equal to am, which is equal to mb. Then what do we get? Let's see. So let's just think about what ax is. So if I go from a to x, then that would be little m minus x. So we'd have something like this. xm squared over ym squared is going to be, let's see, ax I said was m minus x, right? And let's see, so that's ax. What is xb? Let's see, if I go from x all the way over to b, I get x plus m there, or m plus x. So that's what xb is, so this piece right here. And then on bottom, what do I have? I have a by and a ya. So let's see, if I go from b to y, that's going to be little m minus y, and a y to a, that's going to be m plus y. So m minus y, m plus y, which I guess if we sort of think about this, this is the same thing as m squared minus x squared on the top, and m squared minus y squared on the bottom. And xm and ym, kind of think about what those are. X to m and y to m are just the x and the y, right? So we have these all equal to x squared over y squared, which is what we see this to be equal to. Maybe I should put it on that side. Okay, so we have this left-hand side and this right-hand side. We can go ahead and cross multiply. We'll get x squared times m squared minus y squared equal to y squared times m squared minus x squared. X squared m squared minus x squared y squared is going to be y squared m squared minus x squared y squared. These two pieces cancel, and we divide through by m, and we just get x squared equal to y squared. And taking the square root of both sides, we get the absolute value of x equal to the absolute value of y, but both x and y are going to be positive here, so x is equal to y, which is what we wanted to show here, right? So ends the proof. Quite a tour de force. We use the fact 3.14 right off the bat, and then play around with lengths and some substitutions, some slick substitutions to squeeze out the butterfly theorem. And that's really it. That's about all I wanted to show you today. A difficult theorem that seems to require quite a bit of grit and determination to prove, and makes, I guess, quite a lecture when there's just one theorem to prove. Okay, well, I hope that you've enjoyed this, and I'll shoot up another video for the next chapter here in the next couple of days, and I'll see you when I get it back on Monday.